walkthrough in Java Debugger. Here you can see a JVM architecture diagram. A virtual machine is a software implementation of a physical machine. Java was developed with the concept of WORA, write once, run anywhere, which runs on a VM. The compiler compiles the Java file into a java.class file. Then that .class file is input into the JVM, which loads and executes the class file. Below this is a diagram of the architecture of JVM. As shown in this architecture diagram, the JVM is divided into three main subsystems: class loader subsystem, runtime data area, and execution engine. Class loader subsystem. Java's dynamic class loading functionality is handled by the class loader subsystem. It loads and links and initializes the class file when it refers to a class for the first time at runtime, not compile time. Loading. Classes will be loaded by this component: bootstrap class loader, extension class loader, application class loader are the three class loaders that will help in achieving it. Bootstrap class loader, responsible for loading classes from the bootstrap class path, nothing but rt.jar. Highest priority will be given to this loader. Extension class loader, responsible for loading classes which are inside the ext folder, jre /lib. Application class loader, responsible for loading application level class path, mention, environment variable, etc. These class loaders will follow delegation hierarchy algorithm while loading the class files. Linking. Verify. Bytecode verifier will verify whether the generated bytecode is proper or not. If verification fails, we will get the verification error. Prepare. For all static variables, memory will be allocated and assigned with default values. Resolve. All symbolic memory references are replaced with the original references from method area. Initialization. This is the final phase of class loading. Here all static variables will be assigned with the original values and the static block will be executed. Runtime data area. Runtime data area is divided into 5 major components. Method area. All the class level data will be stored here, including static variables. There is only one method area per JVM and it is a shared resource. Heap area. All the objects and their corresponding instance variables and arrays will be stored here. There is also one heap area per JVM. Since the method and heap areas share memory for multiple threads, the data stored is not thread safe. Stack area. For every thread, a separate runtime stack will be created. For every method call, one entry will be made in the stack memory, which is called stack frame. All local variables will be created in the stack memory. The stack area is thread safe since it is not a shared resource. The stack frame is divided into 3 sub-entities. Local variable array related to the method how many local variables are involved, and the corresponding values will be stored here. Operand stack. If any intermediate operation is required to perform, operand stack act as a runtime workspace to perform the operation. Frame data. All symbols corresponding to the method is stored here. In the case of any exception, the catch block information will be maintained in the frame data. PC registers. Each thread will have a separate PC register. To hold the address of current execution instruction. Once the instruction is executed to the PC register will be updated with the next instruction. Native method stacks. Native method stack holds native method information. For every thread, a separate native method stack will be created. Execution engine. The bytecode which is assigned to the runtime data area will be executed by the execution engine. The execution engine reads the bytecode and executes it piece by piece. Interpreter. The interpreter interprets the bytecode faster but executes slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required. Just-in-time compiler. The JIT compiler neutralizes the disadvantage of the interpreter. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the JIT compiler, which compiles the entire bytecode and changes it to native code. This native code will be used directly for repeated method calls, which improve the performance of system. Intermediate code generator produces intermediate code. Code optimizer responsible for optimizing the intermediate code generated above. Target code generator responsible for generating machine code for native code. Profiler, a special component responsible for finding hotspots, that is whether the method called is called multiple times or not. Garbage collector collects and remove unreferenced objects. Garbage collections can be triggered by calling system.gc method, but the execution is not guaranteed. Garbage collection of the JVM collects the objects that are created. Java native interface, JNI. JNI will be interacting with the native method libraries and provides the native libraries required for the execution engine. Native method libraries. This is a collection of the native libraries which is required for the execution engine. Here class file is connected to class loader subsystem. Linking, loading, linking and initialization is inside class loader subsystem. Bootstrap class loader, extension class loader and application class loader is are inside loading. Bootstrap class loader is connected to execution class loader. Extension class loader. Extension class loader is connected to application class loader. Loading is connected to linking. Verify, prepare, and resolve are inside linking. Verify is connected to prepare. Prepare is connected to resolve. Linking is connected to initialization. Class loader subsystem is class loader subsystem interact with runtime data areas. Method area, heap area, stack area, PC registers, and native method stacks are inside runtime data areas. A number of threads are inside stack area. Each thread has stack frame, LVA, local variable array, and operand stack, and frame data inside each thread. There are PC registers for each thread here, and runtime data areas are interacting with execution engine. Interpreter, just-in-time compiler, garbage collections are inside execution engine. Intermediate code generator, code optimizer, target code generator, and profiler are inside just-in-time compiler. Intermediate code generator is connected to code optimizer. Code optimizer is connected to target code generator. Execution engine interacts with native method interface. Runtime data areas are interacting with native method interface. Native method interface interacts with native method library. Now this is the end of my presentation. Thank you very much for watching it.